Yeah, you just gotta be a little.
Okay, so remember, there's a cumulative test on units 1 through 5, in addition to the little bit of integration that we've learned, that'll also be on there. The test is scheduled to be Thursday and Friday. I think I'm just gonna push it to Friday, Monday, just as a precaution. Because even if there isn't a snow day tomorrow, I have a feeling people maybe won't come to school.
I'm already not coming to school tomorrow.
Yeah, so the test will be on Friday, Monday, okay? That way, if we do have school tomorrow, I'll just do more review. And if we don't have school tomorrow, then just shovel stuff or whatever. Okay? Any questions about that? The test will be Friday, Monday. Okay, so today I just thought I would start just by seeing if there's any specific questions, and if there aren't, then I can just do some problems that I have, like that I looked up. Yeah.
Can we just do like 1 or 2 questions on what we did yesterday?
Yeah, what did we do yesterday? I can't remember. Oh, integration involving inverse trig. I don't know if I have any other questions on that, but I could do some delta math problems.
Yeah, let's go back to, will I be allowed to work on my delta math this period?
I can't hear you.
Will I be allowed to work on my delta math this period?
Yeah, sure, you can sit there. Yeah. All right, so
I don't know.
is that what you mean, like do some delta math problems?
Yeah, I don't know, I didn't look yesterday.
Okay, yeah, let's look at it. So,
Also, the way that Delta Math like explains it,
Yeah.
like I was looking at, it's completely different than yours. I don't know.
Yeah, their videos
It didn't
suck.
really click with me, but Delta Math like made a little
Thank
bit
you.
more sense.
oh, really? Okay.
Yeah.
All right,
It's like
uh,
more
Just like
variables
stop
and stuff.
talking halfway.
And my dad works there.
I haven't looked at the videos on this topic.
Yeah, I just like looked at an example and compared it to the way that like you showed us, and they like used like a bunch of variables and stuff. So, yeah, like what we did in the
Okay, so this is the section. So this is a typical problem. So what I would do in this problem, or any problem that involves integration where you suspect it's inverse trig, is figure out which inverse trig function you're like aiming towards, right? So if it's a plus sign in the bottom with no radical, that's inverse tangent. If it's a minus sign in the bottom and there's no term outside, that's probably inverse sine, like this one. And if there's an x out front or some x term out front of the radical, then that's probably an inverse secant. So this is probably an inverse sine problem. So then the next thing you have to do is you have to try and do some arithmetic to this to make it look right. So when I say make it look right, it has to look something like the integral of 1 over the square root of 1 minus u squared du. It has to look something like that. If it doesn't have that form, we can't really integrate it, right? So you got to make it look like that. So what's wrong in this case is that this isn't a 1 and that's a 16. The 9 constant multiple thing, that's completely workable. Like if you have a constant multiple ever in an integral or a derivative, it's just, you just integrate it like a constant multiple. You just take the 9 outside even and just have it be a 1. So the only problems in this case are the 4 and the 16, right? So then you got to think, well, how can I get rid of that 4? Getting rid of the 4 will help me get rid of the 16 in this case. All I need to do is I just need to multiply this by the square root of 1/4. Because if I do that, I'll be able to distribute it into the parentheses or into the radical, and it'll make that 4 into a 1. Does that make sense? But whatever I do on top, I have to do the same thing on the bottom. So I'm going to multiply this by the square root of 1/4 also, which is really just 1/2. So now I'm doing the same thing to both the bottom and the top of the fraction, right? So on the top of the fraction, I just have 9/2, which is a constant multiple. Like I said, it's just 9/2 out front. On the bottom of the fraction, I have the square root of, if I distribute that square root of 1/4, I get 1 minus, if I distribute this, it's going to be 4x squared, right? Which is really 2x squared. So now it looks familiar. Now it looks exactly like what it has to look like, right? And this is an example that I was showing you yesterday where it's the shortcut U substitution method. If I think I'm going to use U substitution, which I think I would here, and I would let U be 2x. So if you think you're going to use U substitution and the U that you're going to pick has a derivative that's just a constant, like 2, then don't really use U substitution. Just take the integral like without it. Like, so this would be 9/2 sine inverse of 2x, but then just divide by that constant in the end. Plus c. So this ends up being 9/4 sine inverse 2x plus c, and that's the answer. Does that make sense? Let's do another one that's not inverse sine. Is everybody okay if I erase this? Okay, so let's just search through until we find one that's not inverse sine, just to give you another example. So, oops, I'm holding it back. Oh yeah, thanks. No problem. All right, so this one looks like it's which of the three? Inverse tangent, because it's plus and there's no radical, right? So again, what's the matter with this is that, well, two things. There's a 9 there and there's a 36 there. Remember, inverse tangent looks like this. The integral of 1 over either x squared plus 1 or 1 plus x squared, right? So in this case, it would be like 1 plus u squared du. It has to look something like that in order for us to work with it, right? So the 9 is really the troublesome thing. How do I get rid of that 9? Yeah, I would multiply the bottom by 1/9, and I'd multiply the top by 1/9 as well. So if I do that, the 9 and the 9 just cancel on top. That's cool. And on the bottom, I have 1 plus 36x squared divided by 9, which is just 4x squared, or 2x squared. So once again, it's that shortcut U substitution thing. This is just going to be inverse tangent of 2x divided by 2 plus c. Yeah.
Can you do the problem that's on the
Yeah, sure.
It's the integral of 6 over x radical x squared minus 36.
X radical x squared minus 36.
So it's a secant.
The dx.
Yeah, with the
Yeah. So normally the secant is the integral of 1 over u radical u squared minus 36. It's that, right?
minus 1, right?
1, not 36. Right.
Yeah, so I did the whole like times 1/6 to radical 136.
Okay. So times 1/6 on the bottom, times 1/6 on top. And think of the 1/6 as being radical 136, so I could distribute it into there instead of thinking of the 1/6 as being part of the x, right? So this ends up being the integral of 1 over x radical. If I distribute the radical 136 in, I get 1/6 x squared minus 1. Is that cool? dx. So then, this is what was confusing me yesterday, actually. So then, there's no, this is not the same term as this, so there's like an issue. For this, I just feel more comfortable doing U substitution. I'm going to do U substitution, okay? So I'm going to say U is 1/6 x, so du is 1/6 dx, so dx is 6 du. So this ends up being 1 over, this is that one, yeah, okay.
Yeah.
So if u is 1/6 x, then x is 6u, right? So this would be like 6u into, or radical of u squared minus 1 times 6 du.
Okay, so the 6 is canceled.
The 6 is canceled, so you get secant inverse of u plus c. So this is just secant inverse of 1/6 x. I don't know why I'm having that mental block that I can't seem to. Every time I get to a problem like this, it seems like it's not going to work like the normal shortcut, but it actually does.
Yeah, that's what happened to me too.
Yeah.
I ended up getting involved just now because I wrote 1/6 x instead of x over 6. Love delta math.
That doesn't do that very often
Yeah.
in Delta Math. It does that a lot in IXL, but right? You haven't come across that a lot of times, have you?
No, just wasn't good to simplify it.
Oh. Maybe it's because you didn't do the absolute value.
Yeah, that's.
You
how
have,
they
you
work.
have to do absolute value.
Yeah.
Yeah.
Yeah, usually like differences in notation like that, you're good.
Yeah.
It's like, it's not any simpler for it to be x over 6.
Yeah. So if this is giving you a hard time, like Maggie said, try and watch the video on Delta Math. It explains it differently apparently. I haven't seen it, but maybe it'll help you. I think it's always good to like look at things different ways. And maybe,
I can do like the secant ones like that way because it just like didn't click for me. And
okay,
they like assign another variable like A and do this like other weird thing, but I don't know how to click, so I was like, all right.
okay, cool. Yeah, that's great. Does that help, John?
Yeah.
Okay. All right, so anybody else have more specific questions or do you want to just go through problems and see what happens?
Sure, let's go through problems.
Okay, so basically all I did, I mean, you can find problems like this too, but basically I just Googled just AP calculus, AB practice test. That's all I did. And it gave, this is what I do to write the test as well. And it just gave me like full length practice exam. So let's just go through it. Like this is non-calculator questions, calculator questions, calculator questions, non-calculator questions. So which ones are more troublesome for you? The non-calculator questions or the calculator questions? Non? Okay, so let's just click on that and just go through some problems. And we can speed through the ones that seem really easy, like this easy derivative of a function. Right, so this would be chain rule, it would be 1 over 2x times 2, right? So it's this answer. Okay.
Can we quickly like review like derivative of like ln?
Yeah. The derivative of ln u is u prime over u. It's 1 over u times u prime. Okay? Is that what you meant?
Yeah.
Just list that, okay. So this one, it says, identify the equation of the tangent line at 0 for this function. So you need a point and a slope, right? So for the point, you substitute in 0. So this is 4 arctan 0. What's arctan of 0? 0, right? It's the angle whose tangent is 0. So this is just 0. And for the slope, it's going to be f prime of x at 0. So this is going to be 4. We've been practicing this really recently, so this should be fresh in your memory. It will be 1 over 2x squared plus 1 times 2, chain rule, right? So this would be 8 over 2x squared plus 1. So f prime of 0, which is the slope, would be 8 over 1. So this would just be it's b, because it passes through the origin with slope 8. So it's b. That make sense? The whole explanation. I've never seen this site before, but it seems pretty good, right? I mean, you can just go through problems and they give you a full explanation of each question. You could do this too. The integral of tangent x plus secant squared x. We're not really capable, oh, we could do this one, actually, we could do this. Why don't you do this one? Any ideas? Who knows? A question like this could be on the test. All we have is basic rules, so it has to be something having to do with basic rules.
Well, I mean, I guess looking at the answers, like saying, like the derivative of ln secant x would just be 1 over secant x, which is just tan x, right? Is that what there is?
The derivative of ln secant x would be
1 over.
1 over secant x times
Yeah,
secant x tan x, yeah. Okay,
so, I mean,
so you think it's B?
I think it's, I mean, it's either B or C.
It's either B or C. Well, which one? What do you think?
That's a good question.
Why do you think it's C?
Intuition.
Well, it's gonna be positive. Right?
Yeah, because the integral of secant squared is positive tangent. So I think it's C too. Yeah, so you can always get the answer of an integral by taking the derivative. And that's what she's saying. She's just saying, just look at the choices and see which one makes sense. The derivative of ln secant would be 1 over secant x times secant x tan x, right? So those would cancel. And the derivative of tangent would be secant squared x. So this is exactly what we started with, so that must be the answer. I was actually thinking of it a little bit differently. I was thinking to try and use the Pythagorean identities to write this in terms of tangent, right? I don't know if that would work. That's not going to work. Forget that. That's not going to work. Because the reason why it's not going to work is this is going to end up being like 1 minus tangent squared x or something like that, or plus, or I don't know, something like that. But then you'll have tangent squared and a tangent, and you're not going to be able to combine them. I was thinking that you're going to be able to combine them eventually. That's not going to work. But this back solving method definitely works with multiple choice questions sometimes, right? If you know what the choices are, you can just differentiate each one quickly in your head, kind of, and definitely rule some of them out, right? To just see which one ends up being the integrand. So it ends up being that. Okay. Next.
If that was if that had been a true response question, though, we would have picked a U, or we would have picked like secant x.
I don't know. I don't know what that method would be. Let's try and think about that. It might be a more sophisticated method we haven't done. It was, what was it? It was,
About 10x plus secant.
let's try what I was saying. So I would have to, like, I don't have all the Pythagorean identities memorized. I have this one memorized. So I would have to take this and then divide everything by cosine squared. The reason I know it's going to be cosine squared is because that's the one that's going to end up giving me secant squared right here, right? So this ends up being tangent squared x plus 1 equals secant squared x. So then this would end up being tangent x plus tangent squared x plus 1 dx. I don't know. I don't know how you do this. It's on an AP. It's on an AB test, so it can't be anything too crazy, but I don't know.
Would you be able to use U substitution here?
Because it'd be
like U plus U squared if you were to use U as tan x?
The problem there is, you're saying let U be tan x, but then the derivative of U doesn't appear here as a factor. So I don't think U substitution would work. I'm trying to think of what the actual answer is. It could be that this problem was just intended for you to look and see which ones have that derivative. So that's a possibility. Just off the top of my head, I'm not sure how you could integrate this like directly and get the answer if this is your response. I'll think about it. but I don't want to waste time just having you stare at me think. So I'll think about it. But for now, I mean, that's a definitely a valid way to do a multiple choice question for sure. This one's not that hard, right? This is going to be inverse tangent. So this is going to be 4 arctan x from 0 to 1. So it's 4 arctan 1 minus 4 arctan 0, right? That's FTC part 1. So the angle whose tangent is 1, what is that? There's no such thing as degrees. It's pi over 4, right? So this is 4 times pi over 4 minus 4 times 0. So the answer is pi. Okay? Is this helpful doing this, what we're doing, or would you rather do something else?
Can we? Oh, sorry.
Yeah, I just have one thing that I was like thinking of when you were like going over,
Yeah.
to go over, but like what were you doing?
I was just gonna ask if we could go over like how, because I don't necessarily know how to say like, oh, the arctangent of 1 is.
Yeah, not off the top of my head too.
That's what you were thinking too?
Yeah.
Okay, yeah, let's do that. So,
Isn't it just something you kind of have to memorize?
kind of, yeah. I mean, that's the way I know it.
Yeah. That's what I-
Yeah, you could look at the triangle. I mean, all right, so I'm trying to think of a concise way of saying this. So you have this triangle and you have this triangle, right? So those are the two triangles you should have memorized. If you're trying to figure out the angle whose tangent is 1, it has to be this one. If it's the angle whose tangent is radical 3 or radical 3 over 3, it has to be this one of these two angles, right? If it's the angle whose sine is radical 2 over 2, you know it's this triangle. If it's the angle whose sine is 1/2 or radical 3 over 2, it's this one. Same thing with cosine. That's basically it. For the reciprocal functions, like if it's the angle whose cotangent is 1, it's this one. If it's the angle whose cotangent is radical 3 or radical 3 over 3, it's this one. If it's the angle whose secant is radical 2, it's this one. If it's the angle whose secant is 2 or 2 radical 3 over 3, it's this one. I mean, you could, if you just have these two triangles memorized, it helps you a lot. In terms of negatives, for that, like if it was like the angle whose sine is negative 1/2, then it becomes a little bit trickier to remember. But the way I remember it is I just remember, what do I remember? I don't know what I remember. I just remember that like arc sine is like in here somewhere. It's either first or fourth quadrant. This is arc sine. And the way I remember that easily is that it can't be these. It's always for the inverse trig functions. It's always either these two quadrants or these two quadrants, right? It can't be these two quadrants if it's arc sine because that doesn't account for any negative values, right? This is positive and positive for sine. So that one's kind of easy to remember, in addition to our cosecant, because it's the same quadrants, right? For the other two, it's a little bit more difficult to remember, although not really. For our cosine, it has to be these two, right? Because if it was these two, then it wouldn't account for negative values. Arc secant is also there. So the only one that's hard to remember is arctangent. And the way I remember that is I just remember like what the graph of arctangent looks like. I know that tangent kind of goes like this, right? Kind of goes like that. So arctangent actually just goes like that. And it's, so this is like 90 and this is negative 90. It's defined between negative 90 and positive 90. So it goes here also.
Well, could you also look at it as like the same way because it's positive in the first and negative in the fourth? Oh, wait, I'm fine.
No, because
Also,
if it was here, it's positive negative, and if it's here, it's positive negative. So that's the only one where there's like some ambiguity involved. You know what I mean? So if they said something like find arc secant of negative 2 radical 3 over 3 or something like that's like the hardest one, kind of, you know what I mean? You would just say, well, I know it has to be in this triangle somewhere. Secant is the reciprocal of cosine, so it has to be the 30-degree angle so that it's 2 over radical 3, right? So I know this is a 30-degree reference angle. So then, since it's our secant, it's in these two quadrants, so it has to be a 30-degree reference angle over here. 5 pi over 6 is the answer. Does that kind of make sense? And then I just remember 30-degree reference angles always have a denominator of 6. 60-degree reference angles have a denominator of 3. And 45-degree reference angles have a denominator of 4. So the 45-degree reference angles are pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. You know what I mean? The 30-degree reference angles are pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. The 60-degree reference angles are pi over 3, 2 pi over 3, 5 pi over 3. Did I miss one? 4 pi over 3, 5 pi over 3. Right? So there's kind of a lot, there's a lot of little things that if you just remember all these little things, you just kind of put them together for each problem and try and figure it out. That's what goes on in my brain. There might be a better way to organize it, but that's kind of the way that it's organized for me. Does that help? Is that what you were looking for, kind of?
Yeah.
Okay. Is that what you were looking for? Yep. Okay. Do you want me to still do problems, or does somebody have an actual specific question? Yeah.
When we did like derivatives as limits, and you had to like find like f of n and like f of x, like that whole thing, can you go over one of those questions?
Yeah, sure, of course. So remember, there's two limit definitions of derivatives. There's the limit as h goes to 0, f of a plus h minus f of a over h. This is f prime of a. And the second one was the limit as x goes to a of f of x minus f of a over x minus a. That's it. Right? So we have two different limit definitions of derivatives. So if they give you a limit, you should always consider that it's possibly one of these. If I saw a limit on an AP exam, the first thing that would come to my mind is, can I evaluate this limit? Do I have elementary methods to do this? Whether it's just evaluate the limit, or whether it's L'Hopital's rule, like you have 0 over 0, is it possible to do it one of those ways? Because if it's possible to do it one of those ways, that's probably the easiest way to do it. If it's not possible to do it, if there's weird trig or exponentials or something strange happening like that, then my mind is going to go to one of these two things. And then your mind should think, well, which of these two things is it? Is it that form of a limit definition, or is it that form of the limit definition? And then evaluate it. So, for example, they might give you something like, find the limit as h goes to 0, and it might be something like, for example, secant squared of pi plus x minus 1 over h, or something like that. So if I'm evaluating this limit, I'm going to be like, there's x is h. This should be h plus h, I plus h. So if I'm evaluating this limit, I'm going to think, well, is it possible to just substitute 0 in? It is. So that's what I'm going to do. I'm going to substitute 0 in and get an answer. This is not a great example, but actually, no, it's an okay example, because if I substitute 0 in, I don't really get an answer. I get 0 over 0. So I'd have to do the L'Hopital's rule in this case, because I get 0 over 0. But anyway, this is also an example of this, right? So if I recognize that this is an example of this, I would have to verify that that's true. The way I would verify that's true is I would think, well, is this really the secant squared of pi? Like, is it that? If it's that, then this is exactly that form, because this is f of pi plus h, this would be f of pi. And in this case, the derivative would be, or the limit would end up being the derivative of secant squared x at pi. That would be the answer of this problem, right? So this is definitely true. The secant of pi is the reciprocal of cosine pi, which would be -1. And if you square that, you get +1. So yeah, this is definitely true. So in my brain, I would confirm that that's true, and then just actually do the problem. So I would say f of x is secant squared x. So f prime of x would be 2 times secant x times secant x tan x. And then I would just substitute in pi. So f prime of pi would be 2 secant pi times secant pi times tangent pi. So this ends up being, well, tangent is sine over cosine, so this is just going to be 0. So the whole thing is just going to be 0, and the answer is 0.
How do you, oh, sorry.
Go ahead.
How do you lay out the test rule again?
Yeah, so L'Hopital's rule says if the limit as x goes to a of p of x equals the limit as x goes to a q of x, and those are both 0, then the limit as x goes to a of p of x over q of x is the limit as x goes to a of p prime of x over q prime of x. That's L'Hopital's rule. So if you're going to use L'Hopital's rule and it's a free response question, remember, in order to use a special theorem like that, you actually have to show that the hypotheses of the theorem are satisfied. So you'd have to verify that this is true, verify that this is true, and then you can just take the derivative of the top, take the derivative of the bottom, and then plug in both the numbers. So in this problem, L'Hopital's rule actually applies. So you can actually use it here. You would say this is equal to the limit as h goes to 0 of, take the derivative of this, which would be 2, small. It would be 2 it would be 2 secant of pi plus h times secant pi plus h times tangent pi plus h. That's the whole derivative of the top over the derivative of the bottom, and then you just plug in 0, which is, you can see it's exactly what we got down here. It ended up being the same thing. Does that make sense? Does that help you here? Okay, so yeah, so you got to remember these two things, and then just remember that this is a possibility. That's the problem. People see a limit, and it's unfamiliar how to evaluate that limit, and they select the choice that says does not exist or something just because they're giving up on the problem. But you always have to remember that this is a possibility. Whenever you see a limit, that's a possibility. Okay, all right, what else? Specific questions, or you want to do a couple more multiple choice? You want to look at a free response? Yeah, okay. I mean, it's possible we won't be able to do free responses that they have, but let's check it out. I don't know how to get to it. This? Nope. That's not it. Return? Nope.
Scroll up.
So are we just gonna review more tomorrow then?
Can I just press an AP
Yeah.
practice test?
Oh yeah, AP practice test. Calculus AB.
I know.
Okay, so let's just look, do you want one with a calculator or without a calculator?
With that.
Okay. Can't do it. Differential equation. Oh, okay, so there's multiple questions. Okay, so here's one. Can't do this one. We haven't learned how to do this process yet. Slope field or a differential equation that looks like that. It's a little strange. By the way, a differential equation is just an expression that says the derivative of something is something. That's a differential equation. So we've kind of done that already, right? I mean, that's kind of what integration is. The derivative of a function is this. What's the function? That's a differential equation. But they get a little more complicated after break. All right, so question 4. Tim and John get an argument over the limit below. Okay. Tim says that the limit, they're very nerdy. They're arguing about limits. Tim says that the limit exists, while John says the limit does not exist. Does this limit exist? Yeah, what's the answer? The answer is 0, because you get 0 on top and you don't get 0 on the bottom if you plug in 0. This is just total substitution. The answer is 0. So A, identify the derivative of x squared using the limit definition. What do they mean by that?
But when you have to use the limit.
Yeah, that's what we just did. So you would take the limit as h goes to 0 of x plus h squared. If we're trying to find just the derivative with respect to x plus h squared minus x squared over h, right? And then evaluate this limit. This is definitely doable. This would be x squared plus 2xh plus h squared minus x squared on top, right? Those cancel. You can factor out an h on top. Those cancel, and now you can plug in 0 for h. You get 2x. We know that's the answer. That's the derivative of x squared, but that's how you get it using the limit definition. Does that make sense? Part B, identify the derivative of sine x using the limit definition. Same process. Okay? You want to do it? Pretty good. C, identify the limit as x goes to 0 of this. How would you identify that limit? What's that? You can't because you get 0 on the bottom. What's that?
The rule that you just used?
Yeah, L'Hopital's rule. This is totally L'Hopital's rule. This would be the limit as x goes to 0 of 2 over cosine x, right? Which would be 2. What's the matter?
I don't know.
You good with that? Okay. And then
That confuses me.
part D, who is correct? Well, this, yeah,
Good old thing.
yeah. I'm not sure what any of this has to do with who's correct, but
Yeah.
yeah. So the guy who said that that does exist is the one who's right. That's it. Okay? That's all we have time for today. So if we have class tomorrow, then we'll just review some more. The test will be Friday and Monday. If we don't have class tomorrow, the test will be Friday and Monday, and we won't review anymore. Okay? Unless, do you want to? We could have the test Monday and Tuesday. I don't really care.
No, I don't want to take a test on Tuesday.
Yeah, no.
Okay, the test will be Friday and Monday. Let me just fix this, sorry.
Yeah.
All right, go.
Okay, so if something you can have, then that, hopefully they'll cancel, and then